So we'll revisit this friction patch example, but this time with more knowledge about friction, so the problem changes a little bit slightly. So we'll have our mass, our starting velocity. We'll have a displacement, or that's how long the friction patch is. And now we're given the coefficient of kinetic friction. We have to determine the velocity of the box after it has reached the end of the friction patch. All right. So the situation is kind of the same. You have the box and it's going, V1 is 8. It's going to run into some friction. We'll just say it's around here. It's going to go, that's going to last for 4 meters. And then by the end of that, so the friction is going to slow it down. So what's this new velocity going to be? The coefficient of kinetic friction is given 0.24. And the mass is given 12 kilograms. Okay, so how can I find the final velocity? How can I find the final velocity? So that seems like that is a kinematics thing. It seems like I want to use the big 5 equations, one of them, to try to get that. But in order to use the big 5 equations, I'm going to need to know 3 other kinematics numbers to plug it into the equation. So I've got one here with the V1, I've got one here with the displacement, but the mass is not part of the big 5, and the coefficient of friction is not part of the big 5, so I actually don't have enough information yet to use one of the big 5 equations. So I'm going to have to take at least another step here to try to figure out one of these other kinematics numbers. And which one is that going to be? It's going to be acceleration. Acceleration is the connection between the big 5 formulas and Newton's second law. So that's going to have to be my first step. So I'm going to make a heading for that, find the acceleration. So in this case, if I have a free body diagram in this box, I have gravity and normal, which are balanced. And then I'll have friction slowing it down. And that's it. There's no applied force. There's nobody pushing this box. It's just friction slowing it down. So when I'm thinking about my net force, because Newton's second law has to do with the net force, since gravity and normal cancel, the net force is the frictional force. So I'll replace net force with the force of friction. And hopefully you're starting to get an idea of how we're going to end up solving for the acceleration here. We're going to get the force of friction, and then we're going to divide it by the mass, and that'll isolate for acceleration. So we're going to use our formula for the force of friction, which is mu times the normal force. That only gives us the magnitude of the force of friction. So on the right side, I'm going to add magnitude bars as well, just to keep things mathematically sound. And I'm going to divide by mass. So I'm going to take mu, multiply it with the normal force, divided by mass. But a big question is, what is the normal force? What is a normal force? Well, in this situation, the normal force is equal to the force of gravity. Just look at the free body diagram. They're equal in magnitude. So I can actually replace the normal force in this case with mg because they are equal. That does not work all of the time, but in this case, just based on the free body diagram, that is the case at this time. The masses can be reduced. So even though I'm given the mass of 12, even if I wasn't given the mass this time, I'd actually still be able to solve this problem because they cancel out. Okay, and now the values. So mu is 0.24 and g is 9.8. I get out my calculator. Giving me 2.352. I'll underline 2 sig figs to match with the previous step. This would be in meters per second squared. So that's the magnitude of the acceleration. I know the direction is going to be to the left because it's going to be the same direction as the net force, which is to the left due to friction. By the way, this result here is a nifty one to remember. That's going to be the acceleration of anything that is slowing down on a horizontal surface due to friction alone. Okay, so it only applies when there's no other kind of forces there changing things up, but it's a nice result. You can speed things up if you remember that. It's not on your formula sheet, so it's just something you'll have to remember if you want to use it. Okay, so now that I have the acceleration, I can go ahead and try to finish the question. I can use it in my big five to solve for the final velocity. So it's easier if I have everything in one column here, just when I'm picking my equations. Now this acceleration I said it's to the left. So I'm actually going to write this as negative to the right, because then I'll have all of my given variables being in terms of to the right. So the formula here will be the fifth of the big five formulas. I don't know why I'm putting those bars there. Let's start over. We're solving for V2 here, so it looks like just square root both sides. Just square root both sides. The negative is going to be inadmissible. Okay, quick look at my signs. My signs are looking good. I've got a negative in there for the acceleration, which is going to make that second term negative. which is what I want because I know this is supposed to slow down. So I need to subtract it from the v1 squared there. So that's good. Okay, go into the calculator here. Square root that, giving me 6.7 after rounding it to 2 sig figs. So the box slows down. So it started at 8 meters per second at the beginning of the friction patch and has slowed down to 6.7 meters per second at the end of the friction patch.